So welcome back to EC Concept once again. So this is the new initiative for TRB Polytechnic questions. Okay, this is the question 2012. Okay, the first question: the static equilibrium implies that. Okay, the static equilibrium implies that forces have zero resultant and zero moment. So this is the option. We know that. To equilibrate a particle. So if you want to equilibrate a particle, we need three translational equilibrium forces. That is, we need to equilibrate force in x direction, force in y direction, force in z direction. We need to equilibrate these three directional forces. Also, we need to equilibrate moment in x direction, moment in z direction, moment in y direction. So total, there are 6 equations which is required to equilibrate a point. That's the meaning. The forces have to zero resultant and zero moment. Okay, these F, X, F, Y, F, Z are the forces. These should have a zero resultant, and this moment also having zero value. Okay, that means the net moment acting on this element is zero. Okay, therefore this is the answer. Answer B is correct. Okay, so this is the answer. Now, the working stress of mild steel is determined from the upper yield stress, ultimate stress, fracture stress, lower yield stress. So answer for this question is a lower yield stress. Based on this lower yield stress only, we are determining the working stress of the mild steel. So for example, this is the stress strain curve for mild steel. This is stress strain. Okay, and this is the stress strain curve. And you will get something like that graph. Okay, this is the stress strain curve. This point is O, origin point, and somewhere here this point is A, and somewhere here this point is B, and this point is C, and this point is C dash. This is a lower yield point. C dash is the lower yield point. Then this is the D. This is the ultimate point. This is the breaking point. Okay. Here, C dash is the lower yield point. C is the upper yield point. C is the upper yield point. Okay. Now, generally, we will take a working stress by considering, by using the factor safety on that yield stress, we will get a working stress. So this is the yield stress, which is equal to 250 for mild steel. See, in this case, this is the yield stress, and this yield stress is corresponding to, that means it is coincides with this yield stress, which is coincides with the lower yield point, meaning the lower yield point and the elastic point. Okay, and the elastic points are lies approximately on the same line. Okay, so the point B is the elastic point. Point A is the proportional limit. Is the proportional limit. Okay, see, we will take the yield stress corresponding to the elastic point. In mild steel, Fy is equal to 15, and moreover, the yield stress which lies approximately on the same line of the lower yield point. So that's why we have taken the working stress of mild steel is determined from the lower yield stress. Lower yield stress. Okay. Now see, this is the yield stress. Now how can you calculate working stress? The working stress will be calculated. It will come somewhere here, and this is using the factor of safety, appropriate factor of safety. Then you will get permissible. That means this one I can write here. Fy divided by factor of safety. So this Fy divided by factor of safety we can write. Fy divided by factor of safety we can write permissible stress, yield stress, not a yield stress, permissible stress, design stress, allowable stress, all are same. Okay, allowable stress, or we can say working stress, all are same. Okay, now next question. The compatibility conditions are essentially required to solve. See, the compatibility condition or the equilibrium conditions are generally used for redundant frame. What is a redundant frame? Redundant means indeterminate frame. Indeterminate frames. Okay. See, there are two method of analysis. One is force method of analysis. Force method of analysis in the structure. Another one is the displacement method of analysis. Displacement method of analysis. Okay. The analysis is broadly classified. There are two. One is a force method. Another one is a displacement method. Okay. Both are used for indeterminate frames or determinate frame also. But here the best one is indeterminate frame. That is a redundant frame. Another name of redundant is indeterminate. Okay. So force method is the first point. Forces are taken as unknown. But here displacements are taken as unknown. And the second one is forces are taken as unknown, displacements are taken as unknown here. And here force method we will use compatibility condition. Compatibility equations used. Here we will use equilibrium equations. Equilibrium equations are used. Okay. So that is the thing. So here the compatibility conditions are essentially required to solve redundant frame. Okay. So this is the compatibility. Then example for force method. Theorem of three moments. Theorem of three moments. The second one is flexibility matrix method. Matrix. Third one, consistent deformation method. Here example, slope deflection method. Second one is moment distribution method. Third one is Canis method. So these all are the some of the important points that you have to keep in your mind while solving the problem. Okay, while solving the TRB questions. And the fourth one is one more thing we can write stiffness matrix method. Okay, the maximum number of unknown forces that can be determined in a concurrent force system equilibrium is. So answer for this question is B. Okay, so here is C, B. How? You have to fix the system of forces on a Cartesian coordinate. This is your y, this is your x. At a point, concurrent system of forces means what? The n number of forces which are acting on a point. If a system of forces are acting on a single point, then we can call it as this is the concurrent system of forces. So the method of solving is first of all, you have to convert these all system into two component. One is sigma v, another one is sigma h. Then the resultant will be calculated by sigma r is equal to, or this resultant simply you can write the resultant r is equal to square root of sigma v square plus sigma h square. Okay. Now, here how many equations are required? Only two. Sigma h is equal to 0, sigma v is equal to 0. So, for the equation that is required to equilibrate this particle, sigma v is equal to 0, sigma h is equal to 0. So, the answer is 2. Okay. Next question. The portion AB is subjected to a force equal to. So, there was a system. They are asking what is the force in AB. So, for that, what we can do, first of all, put sigma h is equal to 0. Assume right side is positive. Then, forces which is acting on this system, okay, you have to calculate. So, draw the free body diagram first. The free body diagram of this is, there was a 100 kilonewton, there was a 100 kilonewton which was acting. There was a 200 kilonewton which was acting. Now, this is the fixed rigid end. Therefore, there was a force. Let me assume this is the RA. We can assume. Then, our right side is positive sigma h. Therefore, RA minus 200 minus 100, which is equal to 0. Therefore, RA is equal to 300 kilonewton. We got RA. Now, they are asking portion AB, what is the force? Okay, if you want to calculate portion AB, the force, you have to cut a section approximately at the center so that we will not confuse. Okay, cut a section on the center of this portion AB. This is A, this is B. Then you have to find out the forces, okay, at this section from left and from the right. So if you take forces from the left, which is acting on this section, is how much? 300, right? That is only RA is acting. And from the right side, what is the net force which was acting at this section? That is 200 plus 100, which is equal to 300. Therefore, this section is now subjected to 300 compression. Okay, so the answer for this question is 300. Okay. Now, if the Poisson's ratio for the material is 0.3, then the ratio of Young's modulus to shear modulus. They are asking Young's modulus to shear modulus. We know that the relation E is equal to 2G 1 plus mu. Okay, they are asking E divided by G, which is equal to 2 into 1 plus 0.3. So is equal to 1.3, 2.6. That is Young's modulus by shear modulus. So answer for this question is B. And also you have to remember some of the relation. E is equal to 2G into 1 plus mu. Next one is E is equal to 3K into 1 minus 2 mu. Next relation E is equal to 9KC divided by 3K, 9KC divided by 3K. Let us take this is C, 9KC plus 3K plus C. The next one is mu is equal to 1 by m is equal to 3K minus 2C divided by 6K plus 2C. Here C or G, both are same. G is equal to C. Both are the representation of the shear modulus. Okay. So you have to keep these formulas in your mind. Very, very important. Next one is, if the ratio of Young's modulus to the bulk modulus is 1.8, then the Poisson's ratio. Therefore, we know that the relation E is equal to 3K 1 minus 2 mu. They said E divided by K, which is equal to 3 into 1 minus 2 mu. What is E by K? 1.8, which is equal to 3 into 1 minus 2 mu. So 1.8, the whole divided by 3 is equal to 1 minus 2 mu. So the answer is, we can write, this is 0.6, 0.6 minus 1 is equal to minus 2 mu. So the answer is 0.4 is equal to 2 mu, 0.2 which is equal to mu. So this is the answer. Therefore, answer for this question is C. Okay. Now, the radius of a Mohr circle for the stress system at a point in a body is equal to what? The radius of the Mohr circle. So there are two stresses are given, but this shear stress is 0. Okay. Before that, I can tell you case 1. Suppose if there are two stresses are acting, sigma y, sigma x, sigma y, then radius of the Mohr circle which is equal to sigma x minus sigma y divided by 2. So this is the radius of the Mohr circle, or this is also called it as tau max. This is also called it as tau max. Radius of the Mohr circle also called as tau max. Case number 2. Okay, here. Okay, case number 2. This is sigma x. This is sigma y, sigma x, and this is sigma y. This is also sigma y, and which is subjected to a shear also tau, 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 tau. Now in this case, radius of Mohr circle, which is equal to square root of sigma x minus sigma y divided by 2 the whole square plus tau square. This is also called as maximum shear stress, tau maximum. Third one, if a system subjected to pure shear stress, okay, pure shear stress, system is subjected to pure shear stress, tau, then the radius of Mohr circle is equal to tau, which is also equal to tau max. Okay, fourth one, if an element which is subjected to only is sigma x, then radius of Mohr circle, which is equal to sigma x divided by 2, which is equal to tau max. And this all three cases, in all three cases, positive means tension, negative is the compressive force. No. Now see this question. The radius of the Mohr circle for the stress system at a point in a body, sigma x, sigma y, but tau is 0. Therefore, this is case number A. So the system is something like that. See, the first sigma x is minus, therefore the force is compression, 160. Here also 160. This is the positive tension, therefore it will go something like that, 350. This is 350. And here the shear stress is 0. Then what is the radius of the Mohr circle? Radius of the Mohr circle R is equal to sigma x minus sigma y divided by 2. So here sigma x is compression, therefore negative 160 minus 350, the whole divided by 2. So the answer for this question is, this is 510, right? Minus 510 divided by 2, which was equal to minus 255. Here always you have to take a modulus. Why? Because the radius is modulus, is a numeral value, it's a positive value. Therefore answer is 255. Answer for this question is A now. Now next one. For a beam carrying a UDL, the strain energy will be maximum in case of the beam is the strain energy maximum. So answer for this is the cantilever, meaning strain energy is directly proportional to deflection. Okay, out of these three beams, cantilever possesses the maximum deflection. Okay, therefore the strain energy maximum is for a cantilever. So option A is correct. Okay, so I can give some of the formula for a strain energy. This also you have to keep in your mind. Okay, for a beam. For example, a cantilever subjected to a point load W, then your strain energy U is equal to W square L cube divided by 6EI. Next one is for cantilever subjected to UDL acting throughout the span, U is equal to W square L power 5 divided by 40 EI. Cantilever beam subjected to moment acting M, this is W, U is equal to M square L by 2 EI. Okay, now simply supported beam subjected to point load at the center, then U is equal to W square L cube divided by 96 EA. then simply supported beam subjected to UTL acting throughout the span, then U is equal to W square L power 5 divided by 240 EI. Then simply supported beam with the couple is acting unlike couple is anti-clockwise, another is anti-clockwise. M, then U is equal to the same formula you have to write M square L by 2 EI. So some of the examination, so this formula directly they will ask you. Okay, next one. So this question is over. Now, two uniform steel rod A and B of same length having diameter so on and so forth subjected to a tensile force so on and so forth respectively. The strain energy in the both rod will be strain energy in both rod. We know that strain energy due to axial force equal to P square L by 2 AE. This is the axial force, right? Strain energy due to axial force. Now, strain energy due to bar A is equal to what? P is P. Same length L, therefore P square by L divided by 2 into what is the area? Pi by 4 D square into E. So this is UA. Similarly, UB is equal to how much? UB is equal to 2P the whole square L divided by 2 into pi by 4 into 2D square because 2D is given into E. Okay, if you simplify this, then 4 P square L divided by this is 4 2 square. Actually this is 2 square. Okay, this is 2 the whole square, 2D the whole square. Therefore 2 square 4 into 2 pi by 4 D square into E. So after solving, you will get a P square L divided by 2 pi by 4 D square E. So the strain energy for both rod UA by UB is equal to 1 now. Both are same. Therefore, answer is equal. Okay. Next question. If the hinged end of a propped cantilever of span L and flexural rigidity EA undergoes a rotation, then the shear force in the beam will be. They are asking the shear force. Okay. So see, they said there was a propped cantilever beam which was subjected to a rotation. Okay, flexural undergo a rotation. So if you give a rotation theta, then this will bend something like that. Okay, so while giving rotation here, then this is the theta, then moment which is corresponding to this rotation is equal to, you know, if the far end is fixed, then this is equal to 4EI by L and theta. The moment which is required to make a rotation theta at this end 4A by L theta. And we know that if you apply some moment at this point, then half of the moment will be carried over on the same direction. This is the anti-clockwise. So this also anti-clockwise. Half of the moment will be carried over here. That is 2EIL by theta. Now, what is the reaction? Here the reactions are something like that. Okay. Here these two moments are in the anti-clockwise. So the reaction shall be developed in such a way that to counteracting this anti-clockwise couple. The couple is anti-clockwise. Therefore, the reaction will be create a moment to counteract this anti-clockwise. To counteract this anti-clockwise, this reaction shall be developed something like that. If you put something like that support reactions, then these two will produce a clockwise couple, right? So that's why I put something like that direction. And this value is equal to summation of these two moments divided by length of the span. Okay. Otherwise, you have to use the equilibrium equations. That is the first principle. From that first principle, you will get an answer. But anyhow, this is the shortcut. You have to add these two, you will get an answer. Therefore, 6EI by L into theta. And this also 6EI by L, sorry, not L, L square. Add these two and divided by length. Understood? So this is L square. Now, they are asking the shear force at this point. At this point, which one is responsible for shear force? This reaction is responsible for shear force. Therefore, this is the reaction which is responsible for shear force at this point. Okay, at this point only they are asking, because we gave a rotation at this point, theta. So therefore, they are asking shear force at this rotation end. Answer is D. Okay, so answer is this one, D. Next one is, I said, for a property cantilever beam, subjected to moment M, this M is required to produce a rotation theta, then here M is equal to 4A by L into theta. Here the half will be transferred theta. But suppose a simply supported beam, apply a unit rotation or a rotation at this point, theta is equal to 1, and the moment which is required to create a rotation, M is equal to 3A by L into theta. That is a difference. If the far end is hinged, then this M is equal to 3A by L. If the far end is fixed, then 4A by L into theta. Okay. Next one. The clockwise moment M's are acting at both ends. Clockwise moment of a uniform simply supported beam. So there was a beam in that a clockwise moment was applied, M. So clockwise moment is applied. Then they are asking slope at the ratio of slope at the ends and slope at the center. Because of this loading, moment loading, this will deflect something like that. This is the deflected shape. So this is the deflected shape, theta. This is the theta. Because these two are equal, therefore these two thetas are same. And also one theta is there. If you draw a tangent, then this is another one theta. Theta at the center. This also theta at the center. Now, after solving, you will get, I can put it, this is theta A. Theta A, this is theta B. Theta A is equal to theta B is equal to end. That is M L by 2EI. Theta C is equal to M L by 4EI. So they are asking the ratio, that is M L by 2EI into M L by 4EI. So answer for this question is 2 now. So answer is C. Okay. Slope at support, and slope at support is ML by 2EA. Slope at center is ML by 4EA. Okay. Next question. If a moment M is applied to the hinged end of a prismatic cantilever, then the moment at the fixed end will be. It's a very interesting question. This is the property cantilever. If you apply a moment M, then this adjacent end, the same direction. This is the anti-clockwise, this is also anti-clockwise. Half of the moment will be carried over. So this is the carryover moment. So therefore answer is m by 2. Suppose you are having a beam, is a simply supported. If you apply m, then there is no moment will be carried over at this point. Here moment is 0 because this is the simply supported end. Suppose another one example. This one is a continuous beam. If you apply moment m here, then the half of the moment will be carried over to the adjacent end. Why it is carried over here? Because this is the intermediate support. For intermediate support, it will be carried over. It fixed support, it will be carried over. But simply supported as a extreme point, it won't carry over. Okay. Then the moment capacity of a section at a plastic hinge. Okay. At a plastic hinge, fully plastic moment will be developed. That is a maximum moment. Okay. The moment capacity of a section at a plastic hinge is a fully plastic moment. Next one. The maximum bending moment under a particular load moving among the several moving loads on a simply supported beam occurs when that point load is placed. When that point load is placed, answer is this one. At a point when the CG of all loads and particular loads are equidistant from the midpoint. For example, let me explain this. There was a, for example, there was a series of loads are acting 100 kilonewton, 200 kilonewton, 150 kilonewton. So these are a series of load. This is acting at a distance of, for example, 2 meter, 2 meter. Okay, first, what we'll do, this is the beam. In order to find out the maximum bending moment, you have to first of all calculate the resultant. The resultant force is, we don't know where it is acting, but okay, first of all, you have to calculate the resultant force. According to variance theorem, the resultant force, we don't know where it is acting, so somewhere or somewhere here acting. The resultant force into x, meaning according to variance theorem, moment of resultant force about any point, I am taking moment about this point, which is equal to sum of moment of system of forces. That is 200 into 2 plus 150 into 2. But this 100 is a line of action about this point, therefore it will not produce any moment. So which is equal to 400, 300, 700 divided by what is the resultant? Resultant is equal to 300, 450. So cancel out these two. So the answer is, this is equal to 1, 4, this equal to 9. So that is a 14 by 9. So we can write now this equal to 1 point, this is 5, 1.5 approximately I am saying 1.5. Therefore, the resultant force is acting somewhere here. Okay, this is the resultant force. Or from here to here, the distance is x. What the point is, the maximum bending moment occur under the load which is nearer to the resultant force. Which is nearer to the resultant force means this is 1.5 and this is 0.5. Therefore, the maximum bending moment is occur under the 200 kilonewton load. And this is the 200 kilonewton load. You have to keep this 200 kilonewton load in such a way that you have to bifurcate this, bisect the beam and bisect the resultant force and the maximum bending moment load, you have to bisect this one, centroid point. Then fix this centroid point on here. Okay, fix this centroid with the centroid of the beam. So therefore, somewhere here is a 200. Okay, this is the load 200. 200. This is 150. Somewhere here is 100. And your resultant force is this one. And the distance between these two is 0.5. And distance between these two is, we know that, 0.25. Okay, 0.25. And this also 0.2. Understood? Now read the statement. Beam occur when the point load is placed. Here the point load, it means under 200 kilonewton load, the maximum bending moment is occur. When the point load is placed at a point when the CG of all loads, CG of all loads is this one. CG of all loads and particular load, this is our particular load, are equidistant from the midpoint, or equidistant from the midpoint. This is the midpoint. These two are kept equidistant from the midpoint. Okay.